Hello and welcome to lecture 14 for the course ECE 257A, Fault-Tolerant Computing. This lecture basically finishes part 6 of the textbook by covering chapters 22 and 24. We covered chapters 21 and 23 in lecture 13. So the first item of business is defining what we mean by degradation management, and then discuss various methods that are available to us for managing degradation. Previously, we talked about degradation allowance, designing the system so that it allows degradations to occur. Now, how do you manage those degradations? Okay. So one of the methods that is widely used for managing degradation is data distribution method. And data distribution methods are of two varieties: data replication and data dispersion. We have talked about this briefly before. Data replication means that we have multiple copies of data items of interest, so that if a site containing one copy of the data malfunctions and that copy becomes inaccessible as a result, we still have other copies that we can access. Data replication is expensive in terms of the amount of redundancy. Data dispersion avoids high redundancy by using various types of coding methods to disperse the data so that we don't totally completely replicate the data, but we cut the data into pieces so that a subset of those pieces are sufficient for recovering data. So it's usually a form of encoding that is used. Okay, so how do we manage replicated data? Previously, we talked about um, having two copies of data, like a main copy and a mirror copy, or having multiple copies, the main copy in various backups. Okay, so methods that we talked about sort of treat one of these copies as special, main copy. And then we have a mirror of that, or we have multiple uh, backup copies. Okay, we don't really need to designate one copy as special, because if one copy is special, then we need protocols to deal with that special copy in a different way than other copies. So for example, we always go to the primary or main copy, and only if that copy is not accessible or we find that it contains errors, we go to the other copies. So now imagine a more symmetric approach. Here I've shown in this diagram 9 copies. So each of those circles is a copy of a particular data file or data item of interest. And they're all the same. None of them is special. So none of them is called primary, and none are called backups. They're all the same. They're 9 copies. And I've logically arranged the 9 copies into a 3 by 3 matrix. This is logical, okay? There's no physical distribution on a 2D array implied here. So the 9 copies are on different sites. Logically, we group the 9 copies into 3 rows and 3 columns. And then we define read and write quorum. So this is just an example of a category of methods. Define read and write quorums. So for example, we can say a right quorum is any three copies that form a row. So the top row constitutes a right quorum, the middle row constitutes a right quorum, and the bottom row constitutes a right quorum. Right quorum means basically when we want to write. So remember that if we have data replicated, when we write, we have to update all the replicas in order to continue operation with the same number of replicas. If we don't update one of the replicas because the site containing it is malfunctioning or is inaccessible, then we no longer have 9 copies, and therefore our system reliability deteriorates. Okay, so when we update data, we have to update all 9 copies. However, it is completely possible that one of the sites holding the data is temporarily inaccessible. It has malfunction, or even it's just busy. It's inundated with a lot of things to do, a lot of communications and other tasks, and therefore it's very slow in responding. Okay, so some of these data pieces, the data copies, are not as easily accessible due to their sites having malfunctioned. Of course, malfunction we assume is temporary. Eventually, the source of malfunction is removed, and that data is brought back into service. It rejoins basically the other copies. However, meanwhile, we want to be able to make progress towards our computation and not have to wait for all the malfunctioning sites to become operational before we continue. So we define write quorums and read quorums. And read quorums in this example are columns. Okay? So we basically, when we update the data, as soon as one of the rows has been updated, we consider our task done. We don't have to wait for the other updates to occur. The other updates can proceed in the background and be done later. Eventually they'll be done, but we don't have to wait for those updates. So let's say the middle row has already been updated, green circles, can continue operations even though the other 6 copies or replicas have not been updated. The reason is that the right quorum being a column, so whenever we want to read data, okay, if we gain access to one of the columns, it's sufficient for us. So if the other 2 columns have malfunctioning units or slow units, we don't care. As long as we can access the 3 units in one column, we are done, because those 3 units in one column are guaranteed to contain the most up-to-date replica. Okay, so if we read, for example, the middle column, it has one of those green circles, which is the most up-to-date. And these updates typically are done by associating them with timestamps, so that the 3 copies that I read, and I don't have to wait for the other replicas, as soon as I read the 3 copies in one column, I start processing them, read the timestamps, identify the copy with the latest timestamp, which is the green one in this example, and then just use that data. Okay, so this basically relieves us from the requirement that whenever we update data, we update all 9 copies. As soon as we have updated 3 copies, so we send the update request to all 9 copies, and we start receiving acknowledgments from those copies that update has been carried out. As soon as we receive 3 acknowledgments from copies that form one logical row, then we know that everything is okay and we can proceed. We don't have to wait for the rest of updates to be carried out. Okay, so this makes data replication. We still have a lot of redundancy. That problem has not been solved. But the problem of malfunctioning sites or slow sites and thereby long or sometimes indefinite waits for data to come back to us has been solved. A similar technique can be used with data dispersion. This is an example that we had before. We have a data file on top, and we encode the data file. We cut it into 6 pieces and encode the 6 pieces using redundancy in such a way that any 2 pieces would be sufficient for reconstructing the data. Okay, so there are 6 pieces. Each of those encoded pieces is perhaps 3 times as large as the original piece that it encodes. And it is done in such a way that any 2 pieces would be sufficient to reconstruct the data. Now, if I define a read quorum and write quorum as constituting 4 of those pieces, okay, so for example, a possible update set are the 4 pieces on the right. Whenever I want to update this data, I try to update all 6 pieces. As soon as I receive acknowledgements that 4 of the pieces have been updated, I don't need to wait for the other 2. Okay, and then a read set can be any 4 set, any 4 copies. And because when I take 4 copies, I write into 4 copies and then read from 4 copies, and there are 6 copies altogether, the 2 sets are guaranteed to have 2 in common. Okay, so if I have updated the 4 pieces on the right and I read the 4 pieces on the left, then the 4 pieces that I read will have 2 most up-to-date pieces that are sufficient for reconstructing the data. Again, it provides me with flexibility. I don't need to wait for all 6 pieces to be properly updated before proceeding. And therefore, if I have malfunctioning sites or congested sites that are slow to react, it doesn't hurt the overall system performance too much. Okay, so that's one idea. that had to do with data. Another thing that we are faced with in distributed systems is reaching agreement between multiple sites that are cooperating to do some task. Okay, this idea is best introduced as a problem, a puzzle-like problem that goes like this. It's called the two generals problem. You may have seen this in other courses. So let me explain what the two generals problem is. So imagine that 2 generals G1 and G2, look at the diagram, and their troops are camped outside an enemy city or territory. And they want to attack and take that territory, but they have to coordinate their actions so that they both attack or neither one attacks, because if only one of them attacks and the other one does not go along, then that one general will be defeated because he won't have enough troops, enough forces to basically defeat the enemy. So the challenge for these 2 generals is that they want to coordinate their actions. Imagine these are, generals from the Byzantine era. They don't have any radio communication, definitely no cell phones. The only way they can communicate is by sending messengers, people. And the nature, the geography of this region is that messengers have to go through the enemy. So this is the setup of the problem. They have to go through the enemy territory to reach the other side. So General 1 decides that tomorrow at noon is a good time to attack, sends a messenger to carry this message to General 2, so that General 2 also attacks tomorrow at noon, and therefore their actions are coordinated. Now this messenger can be captured or can perish as he crosses the enemy territory, or can be delayed because he may have to hide for a while if the conditions are not suitable for crossing without being detected. So the messenger can be delayed beyond tomorrow at noon, or can actually never get through and get to General 2. So General 1 says, let's attack tomorrow at noon, but because he is not sure that General 2 did get this message, okay, he can't attack tomorrow at noon until there is some assurance that General 2 actually is on the same page, so to speak, knows about this decision. Okay, so what to do? Well, an idea that comes to mind is that General 2 sends an acknowledgement, sends another messenger to acknowledge to General 1 that he got the original message and therefore is prepared to attack tomorrow at noon. But the second messenger, the acknowledgement messenger, may not get through. So General 2 has no way of knowing that General 1 got the acknowledgement. And of course, if General 1 does not get the acknowledgement, he will not attack. That's part of the protocol they've agreed on. Okay? So General 2 sitting here has no way of knowing whether General 1 got the acknowledgement. Okay? So what's the solution? Well, you may think, what about General 1 sending another acknowledgement to tell General 2 that he got his first acknowledgement? But again, the same problem arises here because this third messenger may not get through. Okay? And if that third messenger does not get through, then General 2 will not know that General 1 got his acknowledgement, and therefore will not be sure that he will attack. Okay? And you can continue this ad infinitum. Basically, there's no end to it. No matter how many acknowledgements are sent back and forth, there is never complete certainty between the two generals that they are on the same page and that they will both attack tomorrow at noon. Okay, so this is called the two generals problem or the two generals dilemma. Of course, once the number of acknowledgements exceeds a certain number, let's say if you do this for 10 rounds, then it's extremely unlikely that basically the two generals are not both aware of the attack time being tomorrow at noon. So from a practical standpoint, you really can stop after a few rounds of acknowledgement. Practically, that's enough. Okay? So what's the practical relevance of this problem? Imagine that G2 is your bank's central computer where information about accounts are kept. G1 is an ATM where you go to get some money. So you tell the ATM, I want, let's say, $40. Now the ATM communicates with the computer to let it know that you are requesting $40 and to make sure that you have $40 in your account. And if that is the case, then the computer reduces your balance by $40 and the ATM dispenses $40 in cash, and everything is basically, okay, you got your cash, your account, which did have $40 or more in it, was reduced. Your account balance was reduced by $40. Now, these are two independent agents because it's entirely possible for the ATM to dispense the cash and the computer basically malfunctions and does not deduct $40 from your balance. So you want these two to basically be on the same page. Either both of them do their part of this transaction, this one dispenses cash, this one reduces the balance, or neither of them do. Basically, the ATM gives you a message, sorry, but this time I can't dispense the cash. There's some problem. So if the cash is not dispensed and the balance is not reduced, it's okay. If the cash is dispensed and the balance is reduced, it's okay. But you don't want one of them to happen without the other one. You don't want cash to be dispensed without account balance reduced. You don't want account balance reduced without cash being dispensed. Okay, so you see the problem here. Okay, so of course, if your account balance is reduced, but you don't get the cash, you'll be very upset. If the cash is dispensed, but the balance is not reduced, bank will lose money. Although, $40 is not a big deal for the bank, they may actually be happy to tolerate that in order to basically let the transaction go through and the customer not be upset. Okay, so this is the problem of coordinating independent agents in a distributed system under unreliable communication. Even if the communication is completely reliable, you still have that problem that the two agents are independent and one of them can malfunction and not do its part of the transaction. Okay, in order to maintain system consistency, so consistency in the previous example is the account balance and the cash being dispensed being consistent with each other. So maintaining system consistency is done through atomic actions, and there are various ways of performing atomic actions. If you have ever taken an operating systems course, there some of the mechanisms for atomic actions are discussed. Things like locks, for example. You lock a resource so that no other process can access it, perform all the parts of this transaction that is supposed to be atomic, then release the lock. So in the interim, while you have locked the resource, let's say memory location, no other process can access that and get inconsistent or partially completed information. Okay, so I won't say more about this. Practically speaking, we can achieve this by something called two-phase commit protocol. So a two-phase commit protocol is when you have a bunch of sites, one of them is designated as coordinator, although the coordinator can be any one of the sites. It's not a special site, but it's a designated site. And there are participants. So the coordinator and a bunch of participants want to cooperate in performing a transaction. In the previous example, we had two, one coordinator and one participant, but we can have more than one participant. Okay, initially the coordinator and the participant are in the quiet state, basically they're not doing anything with regard to this transaction that we are going to initiate. They may be doing other tasks, but they are quiet with regard to this transaction that we're going to talk about. Then at some point, the coordinator decides to begin executing a transaction. So this is sort of like the notation in a sequential machine, where we have input and output. So a dash means there's no input. This is a spontaneous action. The coordinator spontaneously decides to send a begin message to all participants. So all the participants will receive a begin message from the coordinator, telling them to begin executing this transaction. Okay, the coordinator goes into the wait state and waits for the participants to basically respond. Okay, so a participant receiving a begin message can have two reactions. Basically, it says no, meaning that I'm not ready to participate in this transaction for whatever reason. Okay, so when a participant responds no, it goes into, keep losing my arrow. Okay, it goes into the abort state and aborts that particular transaction and does nothing more. Now, when the coordinator receives a no response from any participant, even one participant, it also goes into the abort state and basically says, because it needs all the participants, it can't do the job without even one of the participants not taking part, so it goes into abort state. And then it sends abort to all the participants, including other ones. So one participant said no, this one aborted the transaction and informed all the other participants to abort as well. Okay, so the other branch is when participant says yes. It goes into a wait state and waits to see what happens. If all the participants say yes to beginning this transaction, then, so yes from all participants, the coordinator sends commit to all, and it goes into the commit state itself. And the waiting participants, when they receive the commit signal from the coordinator, they also commit. Now, commit means they're committing to performing that transaction. Okay, they may not be able to do it right away, but they keep a record that they are committed and basically eventually perform their part of that transaction, like updating a piece of database that they hold locally. And while that piece has not been updated, because this unit is committed to that change, it will not allow any access to that unupdated piece of information. Okay, so this one is committed to making the change. It may not make the change right away, but eventually it will do it, and meanwhile it will not send inconsistent data to other nodes that basically try to access. So if this was, say, the balance of an account being reduced, this node, this participant is committed to that reduction and eventually will reduce the balance. Meanwhile, nobody else can access the old balance, which is inconsistent with the commitment of the node. Okay? So there is a problem with this two-phase commit protocol. I won't go into a lot of details. Basically, there is a chance that participants go into this wait state. So they're waiting there. Meanwhile, the coordinator must send something like a commit or abort for the participants to get out of that wait state. Now, if the coordinator malfunctions, suddenly doesn't work anymore, it will never send a commit or abort, and therefore these participants will be permanently hanged in this wait state, and that's undesirable. Okay, so the three-phase commit protocol takes care of this in most cases. It's still not completely foolproof, but it's better than the two-phase commit. So what has happened here compared to the previous slide is a prepare state has been added between wait and commit. Okay, so when the coordinator receives yes from all participants, it tells everybody to go into the prepare state, not into the commit state. Okay, and this prepare state provides a sort of buffer. You know, the problem with the previous scheme was that a participant that is in the wait state can eventually commit or abort. There's no way for it to know ahead of time whether it will be aborting or committing. It depends on information received from the coordinator. Now the prepare state is not like that. The prepare state eventually the participant or the coordinator will eventually commit, even though they have not committed yet. So the wait state is not adjacent to both an abort state and a commit state. This basically protects the system. So if a unit is in the wait state and it waits there too long, decides to use a watchdog timer to time its presence in the wait state, and then if that time exceeds, it can abort. Okay. Meanwhile, the other units that are in the wait state will not know that this one has aborted, but there are mechanisms to ensure that this information is propagated. And therefore, it's less likely for the system to run into problems. Okay, we also need, so we talked about dependability in data, ensuring data integrity through replication or data dispersion. We can ensure coordination between various sites using these commit protocols. We also need various forms of dependable communication between these sites, and that is needed for both point-to-point messages that are sent from one site to another site and broadcast messages where one site has to broadcast, send a message to all the sites. So some common value, common knowledge should be sent to all the sites. For point-to-point messages, we use encoding, error detecting or correcting code. We use acknowledgements, and we use timeout mechanisms. So timeout basically means if I send a message and don't receive an acknowledgement within a certain amount of time, I assume that the message was lost. I resend the message. Of course, this requires now for us to implement the mechanism to deal with duplicate messages. Because I sent a message, I didn't get an acknowledgement because the message was delayed, or the acknowledgement message was delayed. I send it again, so there's a chance that the recipient will get 2 copies of the message, or that I get 2 copies of acknowledgement for the same message. So if we implement a way of detecting duplicates and ignoring all the extra copies, then this scheme will work well. Now, reliable broadcasts, we won't cover the atomic and causal broadcasts. Those are more advanced topics. Is a broadcast scheme, a broadcasting system, in which a message is guaranteed to be received by all the nodes. So when I send a message in a distributed system to many nodes, these different copies of the message that go to different nodes can experience different latencies. So they are not received by the destinations at the same time. In fact, some of them may temporarily be lost because they're on a site that suffers temporary malfunction. Okay, so eventually the messages must be delivered to all the sites so that when I broadcast something, I can be sure that eventually all the sites will receive that message. Okay, atomic broadcast, I mentioned I won't talk about, also ensures that messages are received in the same order. So if I broadcast message 1 and then broadcast message 2, and the site receives both of them, it should receive M1 before M2, despite different latencies in the network for messages coming from various sources and going to different destinations. Okay, dependable collaboration between a set of nodes is basically the nodes. I mentioned the commit protocol. We also have to have some reasonable amount of confidence that the sites are working. Okay, so it's okay for a site to malfunction temporarily, or a small number of sites to malfunction if we have the capability for tolerating that many malfunctioning sites. We have to be able to sort of manage the overall goal of the system, the overall behavior of the system, despite these malfunctions. So malfunctions with respect to severity are categorized as shown here. Crash malfunction, actually it seems very harsh, a site has crashed, therefore it's not doing anything. It's actually the most benign type of malfunction, because a site that is crashed does not communicate with other sites. Also, because it doesn't communicate, it is incapable of misleading the other sites. Omission is a type of malfunction where a node does not respond to some inputs. So different sites send that node messages. That node responds to some of those, but omits the responses to other nodes. So it's a sort of incomplete functionality. And therefore, for example, if you're trying to accomplish consensus between these sides, it's going to be pretty tricky because it's not reacting in the same way to different sites. Timing malfunctions, the node responds, but either responds too early. Too early is often not a problem, but it can be a problem if you have a certain expectation for the latency. Or too late. So too late is usually a more serious type of timing malfunction. Okay, so sometimes you send it a message, it responds right away. Sometimes it responds with much delay. So it's not reliable in terms of its response time. And finally, the most serious type of malfunction with respect to managing it and being able to ensure correct system operation is Byzantine malfunction. A Byzantine malfunction is when a unit is behaving totally unpredictably. In other words, it follows no pattern, no scheme. Sometimes it doesn't respond to a message, sometimes it responds correctly, sometimes the response is erroneous, sometimes the response is delayed. So this is what happens, for example, when a site is compromised, an adversary takes over and then makes the site behave in the worst possible way with respect to behavior of the rest of the system. In other words, it will send the most damaging, it will show the most damaging kind of behavior to mislead the rest of the system. Okay, so Byzantine malfunctions are the worst kind. crash malfunctions are the most benign kind, that the most the easiest ones to deal with in basically designing robust computations. Okay, this slide I'm gonna skip. It's really not related to the concepts that come later, so you can safely delete it. Okay, another thing that we need in distributed systems, by the way, we did have a course on distributed systems, 254C. It has not been offered for a while, but there is a similar course in the computer science department. So basically, all the topics that I discuss in this lecture are covered in much detail in those distributed systems course. Algorithms for execution on distributed systems in a reliable fashion. Okay, so one of the services that we need in distributed system is a group membership service or protocol. So in a distributed system, we often form groups. Let's say site A, site B, site C form a group to collaborate on executing a particular transaction, and that group may be dissolved later, or it may change membership. We may add sites to that group, may remove. So at any point, sites that are members of a group should be aware of the group's membership. And this group membership must be reliable. In other words, it should be resilient to site malfunctions and also to communication errors. Okay, so there are various protocols that are used for ensuring that it's a type of service that the distributed system provides. You form a group and then you consult that service to find out, which other sites are in the same group as you for the sake of this transaction. And the service is reliable, meaning that despite site malfunctions and communication errors, you can get reliable response to inquiries about group membership. Okay. Another concept is remapping. So once a site malfunctions, we may have to remap the computation so that we avoid using that malfunctioning site. And also load balancing is a related concept. So when sites malfunction, the load of the other site can get out of balance because the load of the malfunctioning site must be distributed to others. And if we are not careful, the load gets out of balance. Therefore, some sites will be overwhelmed with too much load. Others will have light loads, and therefore the system will not work most efficiently. So we need load balancing, meaning the ability to detect this condition that the load is unbalanced and moving tasks between sites in order to rebalance the load. Okay, so here is a very simple example of a computation remapping. So suppose there's a computation that has five segments, and is performed on a linear array so that the computation, part one is performed on this cell, part two here. So these may be processors or special purpose cells. So let's call them processors. Processor one does part of the task, then processor two does the second part, and so on. This blank processor at the end is spare and is normally not used when the other five are working okay. Okay, now if we want to make sure that this task was completed correctly, one approach would be to sort of repeat. So take the output from here, store it, and then repeat the task, take this output and compare it with the first output. That's basically redundancy in time that we examined before. Okay. However, if something is permanently wrong with one of these units, the malfunction is permanent, the second computation may sort of experience the same error, and therefore the error will not be detected. We can remap the computation so that the second version or the second copy of the computation, so this cell or processor is ignored. The first part of the computation is now done by processor 2, the second part by processor 3, and so on. Now, by doing this, if something was wrong in this computation, it's unlikely that this replica, the repetition of that computation, which is done on a different piece of hardware, will experience the same problem, the same error. So it makes it more likely for this duplication in time to detect a problem in the system. So this is just an example. So basically remapping the computation so that it uses different resources compared to the original computation is one way to ensure that the same kind of error in the result does not occur. And the final idea in this chapter is that of modeling degradable systems. So a degradable system, as I mentioned before, can be in intact or fully functional state, or it can be in one of a number of degraded states, less functionality, depending what has been lost. So maybe a processor was lost there, some memory was lost there, and so on. So these are degraded states, and some failed states that we hope never to get into. And the system, as usual, so this is a state space model, transitions between these. So a processor malfunctions, it goes here, then we have repair, take it back there. So the hope is that these degraded states serve as buffers to prevent the system from going into the failed state. So if we manage to repair it from this state back there, then nothing serious happened. It operated for a while in this degraded state. If we happen to go into this perhaps more degraded state, we are still okay, we can still go back. Then eventually, if we either don't detect the degradation or the next malfunction happens too quickly before we have had a chance to carry out these repairs, then we go into failed state, and hopefully this is very unlikely. Okay, so these buffer states here, the more of these buffer states you have, the better off you are, the more likely to avoid transition into these failed states. Okay, notice that here I've basically ignored the possibility that a system can go directly from the intact state to a failed state. And this was the notion of coverage that we discussed in some detail. So for example, I mentioned this state corresponds to one processor malfunctioning. If you don't detect that malfunction, or the system is not able to reconfigure itself in order to tolerate that malfunction, that's the coverage. With high probability it can, but there's a tiny probability that it can't, and therefore we have what is known as a catastrophic malfunction. A malfunction that did not take us into these buffer or degraded state, but took us directly into a failed state. And these are things that we want to avoid if at all possible, or to reduce the probability to an extent that it's no longer a serious threat. Okay, so we talked about how to model this in the state space model that we discussed. You basically have to assign a probability to this direct path, and hopefully that probability will be small enough so that this direct path is almost never taken, and the indirect paths have enough buffer, although that buffer is not infinite. We may, so but there are basically two mechanisms by which such a system fails. One is a catastrophic malfunction. The other one is what we call resource exhaustion. So a processor failed, a second processor failed, a third processor failed. So resources have been exhausted. In other words, they have become so low that the system can no longer perform its function in an acceptable manner. So we can have failure due to catastrophic malfunction because of imperfect coverage, or due to resource exhaustion, where this path is taken and leads to failure. Now, because of this direct path, even if it has a tiny probability, and we discussed this before, it's sometimes not advantageous to add a lot of resources. Okay, a lot of spares, for example, in a redundant system. Because as you add more spares, that reconfiguration mechanism becomes more complex, and therefore the probability of taking this direct path increases. So there's often a sort of a saturation point where adding more resources stops being beneficial because it adds to the system complexity and increases the probability of this catastrophic transition. Okay, so let's now talk a little bit about some concepts on software redundancy from chapter 24. I will cover only a few key ideas in this chapter. And if you are interested, you can read on your own. And it's not necessary that you read them, especially since we don't have exams. But uh, if you have interest in the domain of software, then the ideas in this chapter are perhaps quite relevant to uh, your work or your research if you're doing research on software. Okay, software dependability. Uh, you can read these two examples on your own. They're quite funny. So how is software different from hardware in terms of dependability? Well, one difference is that software unreliability is caused predominantly by design slips and not by operational deviations. Now notice that I'm using here the terms flaw or bug for software rather than fault or error. In the literature, you see references to software fault or software error. In order to, because I'm trying to be very careful with terminology, because the nature of software flaws or bugs are different. They're basically things that exist in the design of the software, not things that can go wrong as the software is being executed. Okay, so it's good to have distinct terms for this. So we can also have hardware flaw or hardware bug, and that's when the hardware design is not correct. Okay, hardware fault, on the other hand, is something that happens. A connection is basically broken, or a transistor burns out, or something like that. Whereas a hardware bug is a design flaw or bug. Okay, this example about 7-Eleven convenience store chain, how they dealt with the year 2K problem is really enlightening. So read it on your own. Okay, so what is software dependability? In other words, do we have something like software reliability just as we had for hardware? Hardware reliability makes sense because we had this probabilistic behavior. We said we have a failure rate lambda for hardware, and then e to the minus lambda t is the reliability of the hardware. And the hardware basically behaves probabilistically. Sometimes it works for a long time. Sometimes it fails in a short time. Its behavior is probabilistic, not deterministic in terms of failures. Okay, do we have the same thing for software? Yeah, for many years in the early days of software development, the consensus was that no, we can't model software in the same way as hardware. In other words, we can't say that we have this exponential reliability for software. Nowadays, the consensus is that we can have this reliability model. So here is basically the way the exponential reliability model works for software. Now, a software usually contains one or more flaws per 1,000 lines of code. Okay, so ideally the software does not have any flaws. It's designed correctly, or if it was not designed correctly to begin with, it's tested and eventually all the flaws are removed. You have perfect software. Well, such a perfect software does not exist. Any piece of software that we come in contact with in our daily lives has flaws in it. These are sometimes called the residual flaws. In other words, when the software is first written, there's a lot of flaws. Testing removes a lot of those. The more obvious ones are removed. Some subtle flaws remain in there and basically sometimes persist to the end of the software's life. So software usually contains one or more flaws per 1,000. So this is basically a measure of quality. If you say that a piece of software has fewer than one flaw per 1,000 lines of code, typically this is a very good piece of software. In other words, it's highly reliable. And Linux has been estimated to have 0.1 flaws per 1,000 lines of code. So it's an extremely reliable piece of software. Okay, now these flaws are typically hidden. In other words, you can run Linux for months or years without hitting one of those flaws, but some combination of conditions in the environment that you're using may expose one of these flaws, in which case the software malfunctions as a result of that flaw. Okay, so we can say that the reliability of a piece of software is exponential e to the minus k of t. F is the number of flaws that are remaining in the software. K is a constant of proportionality. And for example, K can be this small number, 1/10,000, okay? And it's determined experimentally. Of course, we typically do not know the number of flaws in a piece of software because if we knew exactly how many flaws it had, that means we can go and fix those. So the number of flaws is typically an estimate. So if we know that the software has been developed by a process or by a group that has typically one flaw in 1,000 lines of code, and then the software has, let's say, 10,000 lines of code, so we estimate that it has 10 flaws. Okay, so that's the estimated number of flaws in the software. K is this constant that is determined. It's not always this, but depends on Depends on the developer of the software, the level of difficulty in the software, and a number of other factors. So K, basically you can determine it experimentally. K is known, F is estimated. So this will be the reliability equation for that software. And it has been determined experimentally. That's a pretty good estimator for software. In other words, you can run the software and have a pretty good idea of how often it fails or malfunctions. Okay, these residual flaws, basically, so that to give you an idea, a visual understanding of why these flaws exist. Let's say I've written a piece of software that has two inputs, X and Y. So this is the space within which the software operates. Each time I give it an X input and a Y input, I put the software in this point, in this operational point, okay? And this particular piece of software works perfectly for that point. On the other hand, if X and Y put me here, that's one of those hidden flaws. Okay, and the software will produce an incorrect output. Okay, so the red areas are those hidden flaws, and typically there are very few of those, and also they happen for really rare values of X and Y, because if they happened for common values of X and Y, they would have been detected during testing. Okay, so the fact that they went undetected during testing means they're not very common cases. Okay, so when we test software, we tend to concentrate on what is known as corner cases and edge cases. Okay, so for example, extreme values of X are often used in the testing phase to make sure that the software does not fail for those extreme values. Extreme values of Y, extreme on the other side, the minimum value of X. So those edge cases are subjected to more rigorous testing, but still some flaws remain. And as I said, a 10,000 line piece of software, even if it's developed with a process that ensures, let's say, one flaw per 1,000 line of code, will typically have 10 flaws, about 10 flaws in it. So it's not flawless, but those flaws hopefully do not show up very often. Okay. Now, how do we model? In other words, in order to use that exponential equation, we need some basically estimate for the number of flaws. So here is a model of how flaws change as a result of testing. So initially we develop a piece of software. Before testing, it has a certain number of flaws. Again, we don't know the exact number. We estimate that it has a certain number of flaws. Okay? Then as we start testing, in the early days and weeks of testing, we remove a lot of those flaws. We basically run the software. Many of those flaws are caught because we notice that it doesn't produce correct results. We go in and check what happened and find out, here's a flaw, fix it. And then as we remove more and more flaws, it becomes more and more difficult to remove additional flaws. So the rate of flaw removal decreases over time until it becomes very low. So here, within a week, maybe we detect maybe 1 or 2 flaws. At some point, the manufacturer, the seller of the software, decides that the software should be released, because we have hit a point where if we test the software for another 2 months, we may not do much better in terms of removing flaws. So the software is released, and the remaining flaws are basically a flaw of the user of the software, buyer of the software, who will encounter them from time to time. Okay, so this is an optimistic model. It says that the initial flaws, whatever number they were, we remove some of them, and eventually we are left with these residual flaws. More realistic is this model, because as we remove flaws, new flaws are introduced. So any fix basically has some possibility of introducing new flaws in the software. So the number of flaws is basically a moving target. And as we remove more and more flaws, we sort of approach there, and eventually we say, okay, we've removed enough flaws, let's release the software and let the user worry. Of course, the seller will help the user if these flaws surface, try to analyze and find the reason for the malfunction and put patches in. Okay, but we don't delay the release of the software, because otherwise we have to wait for a very long time before the number of residual flaws becomes very small. Okay, so from now on, I'm going to focus on this simpler model. This is already pretty complicated for our discussion. I'm not going to discuss this right-hand side. So there are a bunch of flaws, and we reduce the number of flaws. And the flaw removal rate is a decreasing function. Initially, we remove flaws at a high rate, then that rate decreases and decreases over time. So let's model this process. So F is the number of flaws. Tau is the testing time, how much we have tested. Okay, the rate of flaw removal, so this is the rate, df of tau divided by d tau, is the rate of flaw removal, is a decreasing function of tau. And it's linear. Okay, so this is an assumption to make things manageable, computationally manageable. I'm assuming that this rate declines linearly. And there are two parameters involved that we have to basically determine experimentally. Tau is the time. Okay, so if that's the case, then I can solve this differential equation and find the number of flaws at time tau is some f0, the initial number of flaws. Of course, that's an estimate, as I mentioned, minus this quadratic function of tau. So for example, if the initial number of flaws is 130, it's estimated to be 130, and A is 30, and let's see, B, let's see what we have assumed for B here, 30 tau. So B divided by 2A is 1 over 16. So B divided by 60 is 1 over 16. So it's 60. Let me make sure. So that's 30 tau, 1 minus. So B divided by 2A is 1 over 16. Yeah, B divided by 60 is 1 over 16. So B is 60 over 16, or about 4. Okay. As I said, these companies that develop software from experience, they know what the values of these parameters are for their particular type of software development. And there are also handbooks from which you can consult and read out these parameters. Okay, so basically, if this is the number of flaws, the hazard function, or the failure rate, I mentioned, is k times the number of flaws. So this is the number of flaws from this equation. K is that constant that I mentioned, can be a very small number. And therefore, I now have the reliability expression for this software as a function of how much testing time I put in. The more testing time I put in, the more reliable the software becomes, because there will be fewer residual flaws. Okay, so these are some numbers from an actual product. If we do no testing at all, the mean time to failure is 58 hours. That's basically for tau equal to 0. Then as I increase tau, whatever unit this is, this may be 2 months, 4 months, 6 months, 8 months, or 2 weeks, 4 weeks. Doesn't matter what it is. This is just relative comparing these numbers. So if I do 2 months of testing, let's say, mean time to failure becomes 98. So it increases. And as I increase the amount of testing, mean time to failure increases. And then if it becomes acceptable, that's when I can stop testing. This is long enough, so 8 months of testing is adequate according to this model. Of course, this model is itself approximate, and we cannot depend on it 100%, but it's better than having nothing. Okay, besides software reliability being represented by that exponential, so this is basically an example reliability equation for a piece of software modeled there. It's e to the minus 0.00132t, the reliability. Of course, we have to know what the unit of t is, depending on what units we use for computing this. It can be weeks or months or hours, whatever. When we develop this equation, we have to be aware of what unit of time was used in these calculations. Okay, software also ages. Again, this is very counterintuitive, because software, say word processor, how can it age? Because it's just a bunch of code, and code doesn't change over time. Okay, so what does it mean for software to age? Software ages because, so it does have this basically, so it has infant mortality. Upon release, a software may fail right away, but then it has a constant failure rate, and it has this phenomenon of aging. So what does it mean for software to age? First of all, there can be accumulation of junk in the state part of the software, and this is often reversible through restoration. This is what happens, for example, when software misbehaves, then you use the option of resetting your system to factory setting, meaning that you restore the software to its initial state without all the junk that has been accumulated in the state part of the software. Okay, there's also a second mechanism for aging, and that's the cumulative effect of updates, patches, and the like. As you use a software, from time to time, patches are issued, and you implement those patches. And those patches sort of fix the immediate problem, but they may create other problems. And over time, it's just like, if you have a piece of furniture that you have patched many times over the period you have owned it, it starts looking ugly and undesirable, and you may want to replace it, even though it's still working. It does its job. The same thing happens for software. All these patches will make the software behave unreliably. And therefore, you may want to go with a clean implementation from the beginning. And sometimes software vendors actually do that. They issue a completely new version of the software in which uh, basically they re-implement many parts uh, so that all those patches are not needed anymore. So this is the sense in which software ages: accumulation of junk and also cumulative effect of patches and updates. Okay, so I'm going to skip a bunch of these slides. The formal proof of software, I'm going to skip. Be aware that it exists, but it can usually be done only for toy examples. You can't formally prove an operating system or even a compiler. They're just too complicated. They have too many parts for you to mathematically prove that they are working correctly. But for some simple programs, it's possible to develop mathematical proofs that they're doing the function they're intended to do. Okay, the last idea is software flaw tolerance. So far we have been talking about flaw avoidance and flaw modeling. Basically, try first of all not to have flaws in your software by rigorous testing and so on, or at least model the flaws so that you have an idea of the reliability of the software. For hardware, we talked about tolerance methods. Do we have corresponding techniques for software? And the answer is yes, we do have it, although they are not in common usage. They are actually useful and they are being used, and I'll show you examples of where they're used. Okay, so what is software flaw tolerance? The oldest method was proposed in the early 1970s as n-version programming. So this is very similar to triplication and voting in the case of hardware, except that in the case of software, you don't want to do triplication, because if you take a piece of software, 3 copies of that exact same software will not be useful, because if one of them produces an incorrect result, the other 2 will produce the exact same incorrect result, so the voter will not be of any help here. Okay, so these are what are known as diverse versions of the software. They're not identical copies of the software, but they're diverse versions, and diversity can be in programming teams. Different programming teams implemented those versions, and the programming team can have obviously different personnel and different structure, different methods of software development. Software architecture, they can use different software architectures. They can use different algorithms. In fact, the less coordination between these 3 teams, the better, the more diverse the software becomes. They can even use different programming languages, because an error committed when you implement the software with one programming language may not be committed if you implement it. It's less likely to be committed if you implement it with another programming language. And they can use different verification tools and methods. And finally, they can use diverse data. Okay, so they don't use the same identical data, but diverse data. So they compute 3 versions of the result, and then we vote on them. Now, the first complication compared with the case of hardware is that this voter has to be more complicated, more sophisticated. Because suppose these versions are doing floating point computations, then when they obtain correct results, because they're using different algorithms, different programming languages, errors in the outputs will be different. So the outputs may be correct, but slightly different because floating point computations have errors in them. So the voter cannot just simply compare these three to see if they're identical, or two of them are identical and different from the third one. But it needs to sort of process these inputs and ensure that there is agreement between them. They won't be identical, but they may be in agreement within to the level of error tolerance that we have. Okay. Furthermore, these versions in hardware, if you have 3 copies of a piece of hardware, the latency through them will be the same or almost exactly the same. So the voter can be synchronized so that it allows a certain amount of time for the hardware to finish its job, and then some instance later it does the voting. Here, these versions, because they're diverse, they can take different amounts of time to execute. So there won't be synchronous, but we need to do asynchronous voting. So to summarize, the voter is no longer a simple piece of hardware or software, but it's a pretty sophisticated unit in its own right. But now, if these 3 versions are diverse and something goes wrong, it's unlikely that all 3 versions produce identical errors, or 2 versions even produce identical errors, so that the voter is misled and produces an incorrect result. So that's the idea of n-version programming. In this example, n is equal to 3, but it can be more than 3. Okay, from the very beginning, a lot of people objected to the idea of n-version programming. So here are some of the main objections. Developing programs is already a very expensive and slow process. Why multiply the difficulties by n? Okay, well, a reasonable answer to that is that you cannot produce flawless software, no matter how much money you're willing to spend. So in fact, n-version programming sort of releases you from the requirement of high quality software. So if you produce 5 versions of a software, you can afford to have them of lower quality and still get the correct output by voting on the results. The second objection is that diversity does not ensure independent flaws. It has been documented that multiple programming teams tend to overlook the same details and to fall into identical traps. This is a valid objection. Basically, it's possible that the multiple teams commit the same error based, for example, on the way they were educated or the way they were trained to do programming. It's very possible that even though they're diverse, they commit identical errors, and therefore identical erroneous results will be produced by the software. Now, this criticism is actually a criticism of the modeling use. So if you say, okay, this is a 2 out of 3 system, and I assume that the 3 versions malfunction independently, then of course that objection applies because there will be dependent malfunctions between 2 or more versions. So as long as you model those dependent malfunctions correctly, then you should be okay. So you should not model the n versions as being independent units that malfunction independently. Okay, imperfect specifications can be the source of common flaws. So these programming teams are given a specification of what they should develop, and it's very possible that that specification contains errors. If you give an erroneous specification to 3 teams, then obviously they all will produce bad software. Okay, and the adjudicator, it's usually called the unit at the end, not a voter, because it's really, voting creates the impression that's a simple thing. We call it adjudicator to sort of convey the fact that there's more complexity in it than a simple voter. Okay, N-version programming programs can be modeled by the fault tree analysis method that we saw earlier in the course. So here's an example for a 3-version software. The 3-version software fails or malfunctions if 2 of the 3 versions malfunction independently. So this is 2 out of 3, and this is OR, so this is one path to failure for the N version software. Or if all 3 versions fail, that has some probability that we have to determine experimentally. Or 1 and 2 simultaneously malfunction, 1 and 3, 2 and 3, 2 out of the 3, and we should actually quantify the probability of that happening. So this is all the cases that lead to the N version program failing. Now these dependent malfunctions of 2 units or all 3 units, here's an example from a 4-version software experiment. And so you see that the number of cases, the number of observations where there were no error is pretty large, 322,000, whereas the cases where all 4 malfunctioned is 40. So the probability of this happening is small, and we sort of can quantify it by looking at these numbers. 3 versions malfunctioning together is a bigger number, and so on. Okay, so most likely you have no malfunctions, the bulk of the cases, or a single malfunction, and this is basically designed to tolerate one software malfunction. You get here, you're in trouble, and then these kick in, and the system can fail. These are some applications that I've listed, and the number of versions. So the number of versions typically in practical applications is small, 2, 3, 6. And these, the ones that have a large number of versions, these were mostly academic exercises, like maybe a class of 27 students were given the task of developing a different, so there were 27 versions of a software developed, and then they were used in a 27 version programming scheme. Okay, the last idea that I'll discuss is the recovery block method, which is a sort of dynamic redundancy counterpart to N-version programming, which is the static redundancy version. In other words, all the versions simultaneously compute statically, and then you determine the outcome based on the outputs. In the dynamic redundancy version, only a primary module, primary software, does the computation, and then the output of that is subjected to an acceptance test. So this is sort of the software construct that is used. We run the primary module, subject the output to an acceptance test. If it passes the acceptance test, then we are done. We have correct output. Of course, acceptance tests may not be foolproof. That's a separate topic. But if we have a good acceptance test that can detect problems in the output, then that's it. If the acceptance test is not passed, then we use the first alternate. So the versions are not run concurrently, but one at a time. The primary version is run. If it fails to pass the acceptance test, then this one is run, and so on. A nice thing about this, first of all, these are not run, so we don't use resources for these unless the primary module malfunctions, and we are forced to use those. So that's one advantage. The second advantage is that these alternates, because they're rarely executed, we don't really have to make them as efficient as the primary module. So the example I cite here is that the primary module may be a quicksort routine, whereas the alternates are bubble sort, insertion sort, and so on. These are simpler programs to develop, therefore less likely for us to commit design errors and the software to have flaws in it, but they're less efficient. However, we don't use those very often, therefore it's not a big deal that they're less efficient. Okay, I mentioned that acceptance test is a challenge to develop. We don't always have good acceptance tests. So for example, if you compute the square root of a number, the acceptance test may be to square the result and check to see if it matches the original number. Now, if squaring is simpler than square rooting, then this is good, because the acceptance test is of lower complexity than the main computation. But that's not always the case. So it's a challenge to develop that acceptance test. And finally, many years ago, I developed sort of a method to combine the idea of n-version programming with acceptance testing. And let me just show you the next slide. These are some examples. So this is a 5-version program. 5-version, voting, and then as long as 3 out of the 5 agree, then that's the output. If there is no agreement between 3, then we have failure. So here's an alternative to 5-version programming. There are 3 versions that are run here. There's a 4th version here, and there's an acceptance test here. So an acceptance test, let's say, is of the same order of complexity as one of these versions. So in terms of complexity, the 2 schemes are the same. However, this scheme only runs 3 of the versions, and if all 3 agree, which is the usual case, then we are done. So the other 2 versions are not even executed. So we save on execution time. If 2 versions agree, these 2, let's say, agree, and the 3rd one disagrees, then we can subject. So here we have less confidence in the correctness. Only 2 agree, and we have 5 versions, okay? So we can subject that output that was agreed upon by these 2 to an acceptance test and become more or less confident that that's the correct output. Okay? If none of these happens, in other words, there isn't 3-way agreement or 2-way agreement with the passing of acceptance tests, in other words, there's failure here, then we execute the 4th version and take the output of that as the overall output. Now, because here we had some malfunctions already, in other words, either one of these failed and the acceptance test failed, or 2 of these failed, then this one must be correct, because we assume when we use 5-version programming, there are no more than 3 malfunctions. No more than 2 malfunctions. In other words, the majority of these provide the correct output, okay? So if we already had 2 malfunctions here, then we can assume that this 4th version is correct, and we use its output. Okay, now this lecture became a little bit longer than the usual. I'm going to stop at this point, and stay safe until the next lecture. Bye.